after the derivation following Planck's postulates, yes, let us call them postulates. The fact that Planck shifted from continuous energy to discrete energy, the fact that he used the same statistics of Boltzmann, but he replaced the integration by summation. We saw that the energy density falling within wavelength range lambda and lambda plus d lambda is given by this expression. Okay, so this is Planck's radiation law in terms of wavelength. And we can similarly find the radiation law in terms of, okay, this is the radiation law in terms of wavelength, and this is the radiation law in terms of frequency. So basically we had derived the radiation law in terms of frequency, and then using the relation between wavelength and frequency, we wrote down the radiation law in terms of wavelength. And then finally we saw that under suitable limits, that is, if you take a look at the formula in terms of frequency, then we can see that this E nu d nu, the energy density within the frequency range nu and nu plus d nu, is some constant with nu square and h nu by, just a second, e to the power h nu by kt minus 1 into d nu. Okay, so there will be a nu square over here. Now, so now we know that if nu tends to 0, then h nu by kt will tend to 0. Okay, that will lead to e to the power h nu by kt. The series will be of the form 1 plus h nu by kt. Other higher order terms we can neglect because nu is very small, and therefore the expression of E nu becomes of this form, h nu by 1 plus h nu by kt minus 1. So basically this goes to kt. Okay, again when nu tends to infinity, now E tends to kt means it is following the classical equipartition law, and we know that when we are in the small frequency range, then the equipartition law is maintained. It is only when we go to high frequency range that the equipartition law is not maintained, and that is when the experimental curve is not in agreement with the classical theories. And then we see that at nu tends to infinity, h nu by kt tends to infinity, so that e to the power h nu by kt tends to infinity, and E nu then becomes of the order of 0 because we have infinity in the denominator. So now we have a curve. This Planck's curve is given by the blue curve, and we know that the experimental curve also looks exactly similar. Okay, so the assumption of Planck that energy is absorbed or emitted in discrete fashion rather than continuous fashion in terms as integral multiples of the smallest energy unit, that is h nu. When the derivation is done following that assumption, it is seen that the experimental and theoretical curves exactly match each other. Okay. Next, now Planck's radiation law in terms of wavelength looks like this: E lambda d lambda equal to 8 pi hc by lambda to the power 5 d lambda by e to the power hc by lambda kt minus 1. Now from this law we will now see that the classical laws of Rayleigh-Jeans, Wien and Stefan Boltzmann are all obtained as simple mathematical consequences. Okay, so we will now try to derive each of the classical laws from Planck's radiation law, thereby understanding the fact that Planck's law is basically a general law applicable under all circumstances, and the classical laws are only special cases of Planck's law. Okay, so that is the sort of our goal right now. So first we will see how Rayleigh-Jean's law is obtained from Planck's law. If you remember that Rayleigh-Jean's law Rayleigh-Jean's law led to ultraviolet catastrophe. However, it is not that Rayleigh-Jean's law is not in agreement with the experimental curve throughout. It is in agreement with the experimental curve, but not throughout the range of lambda or nu, whatever you are plotting it against. So let us see what happens for long wavelengths. Long wavelengths means small frequencies. If you look at Planck's law, then for long wavelengths, this denominator here, hc by lambda kt, the power of the exponential, goes to 0 because lambda is now very large. So it is in the denominator. So hc by lambda kt tends to 0. So e to the power hc by lambda kt will tend to 1 plus hc by lambda kt, but this is the series which we can replace by 1 plus hc by lambda kt because the higher order terms can be neglected as hc by lambda kt is small. So the expression E lambda d lambda becomes 8 pi hc by lambda to the power 5 d lambda by 1 plus hc by lambda kt minus 1. So 1 and 1 goes. So what you are left with is, you can do this is simple algebra. 8 pi kt goes up, hc and hc cancels out, lambda and lambda to the power 5 cancels out to give you lambda to the power 4. So 8 pi kt by lambda to the power 4 d lambda. So see, we have already got the 1 by lambda to the power 4 relation, which is the relation followed in the Rayleigh-Jean's law. Okay, so basically Rayleigh-Jean's law tells us that energy density is of the order of 1 by lambda to the power 4. It goes as 1 by lambda to the power 4, which is why we saw that it was in agreement at large wavelengths, but trouble occurred when we came to small wavelengths. When this blew up, when lambda is small, this term blows up and we attain ultraviolet catastrophe. Okay, so the first case we see that from the expression of Planck's radiation law in terms of wavelength, if we take the case of long wavelengths where Rayleigh-Jean's law is valid, the Planck's radiation law expression simply boils down as a mathematical consequence to the expression of Rayleigh-Jean's law. Okay, so we can say that Rayleigh-Jean's law is a special case of Planck's law when the radiation is large or when frequency is small. Next, we will see how to derive Wien's radiation formula from Planck's law. So now we see what happens for small wavelengths, that is for large frequencies. Small wavelengths means large frequencies. The term hc by lambda kt tends to infinity, right? Small wavelength, so this term will tend to infinity. So e to the power hc by lambda kt minus 1 is much larger than 1, so we can write this as e to the power hc by lambda kt just. So the expression E lambda d lambda becomes equal to 8 pi hc by lambda to the power 5 d lambda by e to the power hc by lambda kt minus 1 was the expression that now with this replacement at small wavelengths becomes 8 pi hc by lambda to the power 5 e to the power minus hc by lambda kt d lambda, which again I hope you can identify is Wien's radiation formula, the 1 by lambda to the power 5 dependence. Okay, so basically we are getting E lambda d lambda as some constant by lambda to the power 5, e to the power some constant by lambda t d lambda. Okay, this is exactly the form of Wien's law of energy distribution, which we know is valid for small wavelengths. So we knew earlier while doing our discussion of classical theories of radiation that Rayleigh-Jean's law was valid for large wavelengths and Wien's radiation law was valid for small wavelengths. And taking the limits lambda to infinity or lambda to 0 in Planck's distribution law, we get back both Rayleigh-Jean's law and Wien's radiation law. Once again proving that Planck's radiation formula is the most general radiation formula. Now at constant temperature, the wavelength lambda max at which the energy density becomes maximum is obtained from Planck's formula, right? We know that the second law of Wien, that is Wien's displacement law, which is an experimental law, gives us a relation between the maximum value of lambda, or rather the value of lambda at which energy density becomes maximum, with the temperature. We know lambda mt equal to constant is Wien's displacement law. Okay, so here we see, so we will get the maximum or minimum of energy by taking E lambda d lambda equal to 0. So, and seeing what happens at lambda equal to lambda max. Now, if you take log on both sides of Planck's energy expression, which is this in terms of wavelength, and we take log on both sides, we have log E lambda equal to log 8 by hc minus 5 log lambda minus log of this term e to the power hc by lambda kt minus 1. If you differentiate this with respect to lambda, what do you get? 1 by E lambda d E lambda d lambda equal to, this is constant, so 0, minus 5 by lambda minus 1 by e to the power hc by lambda kt minus 1 e to the power hc by lambda kt into minus hc by lambda square kt. Okay, I hope this step is clear to everybody. You are just taking the log and then differentiating with respect to lambda. So what do we have? 1 by E lambda d E lambda d lambda equal to 1 by lambda into minus 5 plus e to the power hc by lambda kt divided by e to the power hc by lambda kt minus 1 whole into hc by lambda kt. Now at lambda equal to lambda max, we must have d E lambda d lambda equal to 0. The derivative must be 0 because we get either maximum or minimum. Okay, so this expression, since this is 0, so this expression must be 0. So what do we get? Hc by, let us take hc by lambda max kt equal to x, so that in this expression we can write 5 minus 5 plus x e to the power x by x minus 1 into, yes, this is x. So x e to the power x by x minus 1 minus 5 equal to 0. So x e to the power x minus 1 equal to 5. Now this is basically a transcendental equation, and this needs to be solved numerically or graphically. All of you, now that you have done computer programs, you know how equations can be solved numerically. Although at that point of time it was done not using computers but using numerical analysis. However, we can now write down that the value of x by solving this transcendental equation comes out to be x equal to 4.9651. Okay, so we have hc by lambda max kt equal to x, which we took as x as 4.9651. which means lambda max t equal to hc by xk. If you put the values of h and c and k along with the value of x that is obtained from the solution, then we see that lambda max t is equal to 2.898 into 10 to the power minus 3 meter Kelvin. Okay, this is basically Wien's displacement law. Wien's displacement law gives us the fact that lambda max into absolute temperature of the body is equal to a constant. That exactly is Wien's displacement law, and we can see that doing some mathematical manipulation to Planck's radiation law in terms of wavelength, we can come back to the expression of Wien's displacement. Okay. So now we are left with Stefan-Boltzmann law, and this is the last one. So as I told you, it will be a very short class, because after this I will have to start Bose-Einstein statistics, which it's not really, it doesn't make sense to start Bose-Einstein statistics like that. So I'll just explain how Stefan-Boltzmann law is derived, and then I leave it today. So we know that the energy density of the total radiation of all wavelengths in a black body enclosure at temperature T is given by this, right? E lambda d lambda is giving you the energy density within a range lambda and lambda plus d lambda. So to get the entire energy, we need to integrate from 0 to infinity, where wavelength ranges from 0 to infinity. Remember, here you can say that, ma'am, why are we integrating? Because we said just now that we will be we have switched from continuous to discrete. We are integrating because we are integrating over wavelength. The wavelength can change continuously, we know that, but energy cannot change. We cannot integrate over energy. Energy is a discrete function, but wavelength can change in continuously. Okay, and here you can see that we are writing energy in terms of the wavelength. Okay, so okay, so this is the integration that we have to perform. Now again, let us substitute x equal to hc by lambda kt. So lambda becomes equal to hc by x kt. So d lambda equal to minus hc by x square kt dx. Now look at these boundary conditions. At lambda tends to infinity, because of this substitution that we made, at lambda tends to 0, x will tend to infinity, and at lambda tends to infinity, x will tend to 0. This is clear from the substitution of x that we made. So now if we change the variable of the integral from an integral in terms of lambda to an integral in terms of x, what do we have? We know at lambda tends to 0, x tends to infinity, and at lambda tends to infinity, x tends to 0. So our integral is now from infinity to 0. 8 by hc ktx by hc whole to the power 5 into 1 by e to the power x minus 1 whole into hc by ktx square with a minus in front into dx. Okay, you can do this substitution for yourself and see that this is the expression that comes. See if I have done any mistake. কারণ আমাকে টাইপ করে করতে হয় তো টাইপোতে মিস্টেক হয়ে যেতে পারে. So if I make any mistake, then please inform me. So what do we have? We have 8 by k to the power 4 t to the power 4 outside, and we have downstairs we have h cube. This is hc whole to the power 5, and we have hc over here, hc over here. So downstairs we have h cube c cube. Integration infinity to 0, x cube, because we have an x square here, so x cube remains, e to the power x minus 1 dx. Okay, so this comes out to be 8 by k to the power 4 t to the power 4 h cube c cube integration 0 to infinity x cube by e to the power x minus 1 dx. So the minus sign goes when you change the boundaries. It was from infinity to 0, so you change the boundary from 0 to infinity and the minus sign goes. Just keep noting that we have already got the t to the power 4 dependence. Everything else is constant, right? We have to evaluate this integral, of course. Other than that, the t to the power 4 dependence of Stefan's law is already obtained. Okay, so it can be shown that the value of this integral is pi to the power 4 by 15. Okay, you don't need to work this out. If you're interested, you can work it out. Otherwise, you can just use this value. It will give you a gamma function, and you can show that the value of this integral comes out to be pi to the power 4 by 15. Okay, so the energy, the total energy is equal to, see, several constants, 8 pi, we have another pi to the power 4, so 8 pi to the power 5, k is Boltzmann constant, k to the power 4 by 15 h cube c cube into t to the power 4. Okay, so we write it like this, 4 by c, just we are just doing some algebra over here. 8 I am writing as 4 into 2, so I am taking outside c from here, so I am writing 4 by c into 2 pi to the power 5 k to the power 4 by 15 h cube c square whole into t to the power 4. Okay. Now, it can be shown that for a black body, the total emissive power is related to the energy density like this. Okay. Energy density multiplied by c by 4, where c is the velocity of light. Okay. So, the energy density can be written as equal to E by C, 4 by C epsilon. Alright. So, now we have in this expression, if we write in this expression E equal to 4E by C, then C, 4 and 4 goes off. E is equal to 2 pi k to the power 4, 15 h cube c square whole to the power, whole into t to the power 4. So, a constant into t to the power 4. So, the energy density that we now call it is equal to sigma t to the power 4. Okay. Sigma is 2 pi to the power 5 k to the power 4 15 h cube c cube, and this is our Stefan constant. Okay, and this law that emissive power of a black body which emits all kinds of radiation at a particular temperature is proportional to 4th power of the temperature, and the proportionality constant sigma is called Stefan's constant. So this is a very, very important law, and we know that later on this is the form of the law that Stefan had proposed. Later on, of course, then the temperature of the surroundings was also taken into account, and the law took the form epsilon equal to sigma t minus t0 whole to the power 4. Okay, so we obtain Stefan-Boltzmann law from Planck's radiation law. Now, this is just some trivia that I gathered from Resnick's book and Feynman's book. See, just a second, I'll just get the book once. Okay. See, experimentally obtained value of Stefan's constant is this. Okay, 5.67 10 to the power minus 8 watt per meter square Kelvin to the power 4. And Boltzmann constant that was known at that time was 1.38 10 to the power minus 23 joule per Kelvin, and the velocity of light is of course this 3 into 10 to the power 8 meter per second. Okay. Now the value of Stefan's constant that was known at that point of time, this value, the 5.67 10 to the power minus 8 value, this was obtained later on experimentally. Okay, but the value of Stefan's constant that was known at that point of time was this 5.79 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. So using these values in the expression of sigma, the constant that is there in the Stefan's law as derived from Planck's radiation law, if you put these values, then the value of H comes out to be 6.57 into 10 to the power minus 34 joule seconds. And it is interesting to note that this was the first calculated value of H. Remember, I had told you this in our previous class that Planck had taken the constant to be H, and when he got his radiation law, he tried to fit the radiation law to the experimental curve, and in doing so, he had to arbitrarily choose values of h, and he saw that h has to be very small in order that the radiation law fits the experimental curve, and then the value of h for which he got the best fit of the experimental curve is the value of h that he had selected for his radiation law. Because in a law, if you have a constant, then you have to give the value of the constant. So the value of the constant that Planck gave was the value that gave him the best fit to the experimental curve. This value of h, when Stefan's law was derived from Planck's radiation law, and this expression of Stefan's constant was found in terms of h, k and c, the values of sigma, k and c being already known, the values that were known at that particular point of time, using those h was determined, and it was found to be of this value 6.57. See, this is not exactly accurate, but you are already getting the 10 to the power minus 34 order in Joule 2nd. So this was the first calculated value of h. We know now that mostly the accepted value of h is 6.62 into 10 to the power minus 34 joule second, and if you put this value of h in this expression for obtaining the values of the energy density, then it is seen that the theoretical distribution agree exactly with the experimental curves over the entire range of wavelengths. If there was a little bit of error bar in the fitting of Planck, now when the more accepted value of h obtained from other experiments are used in the expression, that gives us an exactly fitting curve for the experimental values. Okay, so you have to remember here that the success of Planck's hypothesis in explaining the distribution of energy in the spectrum of black body was the beginning of quantum mechanics. Okay, this marks the beginning. After this, of course, there was photoelectric effect, there was Compton effect, etc. Those were studied extensively, and then Schrödinger brought about his quantum mechanics or wave mechanics. Then we have Heisenberg's matrix mechanics, etc. Then that developed into quantum field theory, which those of you who will be studying MSc master degree will be studying. It's a very, very interesting subject, quantum field theory. Okay, it just opens up an entirely new vista in front of you when you study quantum field theory. However, this, by performing this experiment, this exercise, not experiment, I shouldn't say experiment, I don't know when we will again perform experiments, but by performing this exercise, the way we followed Planck's footsteps to derive Planck's radiation law, used Planck's radiation law to see how the discrepancies of the classical theories were removed, and the fact that Planck's radiation law fitted the experimental curve, how, as I described to you, how he used the ad hoc assumption, and then he got the ad hoc assumption that energy is proportional to nu, energy is proportional to nu, the frequency, and the proportionality constant is h, and how he used different values of h, by trial and error method to fit the experimental curve. You have to keep in mind that all this is happening in 1900, when there are no computers, no GNU plots, no pi plots. So he is doing everything by hand, no calculators. So everything is done on pen and paper, and in head, of course, in his head. So you have to appreciate the the beauty of the entire process. Okay, and then he gets a best fit. The value of h is that what he takes that gives him the best fit of the experimental curve. And then we see that the classical theories that were already proposed to explain blackbody radiation experimental curves and which failed under different circumstances, not for the entire range, but for different parts of the range. Those classical theories can be obtained from Planck's radiation law just as mathematical consequences by putting lambda tends to 0, by putting lambda tends to infinity. And then he also proves Stefan's law, which was again not obeyed if you take Rayleigh-Jean's law, the expression of Rayleigh-Jean's law. So Rayleigh-Jean's law, Wien's distribution law, Wien's displacement law, and Stefan's law, the four classical laws, are all obtained under suitable limits from Planck's radiation law. And then when we finally obtain Stefan's law and denote Stefan's constant in terms of h, k, and c, and since we know the experimentally found value of sigma from Stefan's experiment, and all of you have also performed the Stefan's law experiment in the laboratory, you know what an easy experiment it is. So using that value of sigma, we get a value of h, which is the first calculated value of h. And then there are other experiments, other theories that further develop on the accuracy of h, and the now widely accepted value of h that we use, 6.62 into 10 to the power minus 34, if we use that in Planck's radiation formula, it is found that the experimental curve of blackbody radiation is exactly fitted by Planck's radiation. So this is sort of almost an algorithm. You have to understand the scheme, the step-by-step procedure, to come to the final form of the law, and then the consequence of the law. So you have and not only going through the mathematics, but understanding the scheme is also very, very important. Okay, if you sit and carefully go through the steps and get into your head the scheme, then the mathematical derivation also becomes easy and the concept totally sits in your head and you will not forget it in any time in near future. Okay, so that's all I have to say today. If you have any questions regarding this, you can ask me now.